Hi everyone, my name is Jade. I'm a student here at the University of Maryland, and today I'll be talking about ongoing work done on classical non-abelian thermodynamics. This is done in conjunction with Alexander LeSchack and Nicole Younger-Halpern, as well as other collaborators who may join the project. I'd like to start by describing the field that I work in, quantum thermodynamics. In the 1800s, the development of engines and industrial machines motivated scientists to understand how energy is transformed. How do we get useful work out of certain processes? Thermodynamics was born out of these questions. With the onset of quantum theory, we have to extend thermodynamic laws to quantum systems. Let's now turn to non-commutation. We often encounter non-commutation in quantum theory, where two observables do not commute if we cannot measure them simultaneously. In a thermodynamic system, this will look like a small system inside an environment E. There's a quantity Q sub A conserved by the system and the environment. This quantity can be something like energy, spin, or particle number. There's another such quantity, Q sub B. They're being exchanged between the system and the environment. In classical thermodynamics, we often implicitly assume that these quantities commute with each other, that we can measure them at the same time. In quantum thermodynamics, that was also the assumption for a very long time. But because we often encounter non-commutation in quantum theory, we need to ask the question, what happens if Q sub A and Q sub B do not commute? That is equivalent to saying that the system has a non-abelian symmetry. And what we find is that in systems with non-commuting conserved quantities, thermodynamic phenomena tend to change. So let's be more specific about our quantum system. We can take a chain of n quantum particles and take a small subset of them to be the system. The rest of them are the environment. They're exchanging spin components. And as I've said, spin components do not commute with each other. So spin x, spin y, and spin z cannot be measured simultaneously. What's the classical analog of this? The title of my talk is Classical Non-Abelian Thermodynamics. So the classical analog of a quantum spin is just a spinning top. You can take your favorite spinning top, a Beyblade or a dreidel, and you can imagine the same system here. Each spinning top has angular momentum components, x, y, and z, but these are just numbers. They're not quantum operators, so they will commute. It does not matter in which order you measure them, and they can be measured simultaneously. So then where does non-commutation come in? It's in the fact that angular momentum is the generator of rotations, and rotations in three-dimensional space do not commute. If I take a rigid body and I rotate it around the z-axis and then the x-axis, that's not the same thing as first rotating it around the x-axis and then the z-axis. You'll end up somewhere different in physical space. So the changed thermodynamic phenomena that I'm interested in, that we've seen in quantum systems with non-commuting conserved quantities, is local interaction's ability to affect global evolution. So local interaction is an operation that only affects some of your quantum particles or spinning tops in this case. So it'll only affect 2 or 3, not all of them. Whereas a global evolution can be applied to all the particles in your system. For quantum systems, it was found that local interactions without any restrictions can implement all global evolution. So you have a global evolution that operates on your system, some combination of local interactions will achieve the exact same effect. However, when you apply a restriction in the form of a symmetry and moreover a non-abelian symmetry, this is no longer the case. For some global evolution, we can't use some combination of local interactions to realize it. My work this summer focused on just the local interactions. Consider the classical analog of a two-body interaction obeying a non-abelian symmetry. How do two tops evolve under this interaction? Here are the two tops, A and B. The potential energy interaction term between them is the dot product of the orientation position vectors of the tops. So the long axis of the top, that vector in space, we take the dot product. The kinetic energy of this system is just the sum of the individual energies of the kinetic energies of the tops. What we can do is solve for the dynamics of each top using the Euler-Lagrange equations. The Lagrangian is just the potential energy subtracted from the kinetic energy, and the Euler-Lagrange equations are given by that formula, where our generalized coordinates in this case are Euler angles, which connect a rotating frame, our tops are rotating, to a static frame that we can view both tops in. And what we find is that two tops beginning with their long axes pointed in an arbitrary direction precess about the axis that bisects the angle between them. So for initial starting positions like these, what happens is this orange vector represents the axis that bisects the angle between them. The two vectors, once this potential energy interaction is turned on, will precess around it. And this should make sense because what is a dot product? A dot product is the magnitude of two vectors multiplied together by the cosine of the angle between them. And it's also a geometric measure of how much the two vectors overlap. So how much do two vectors overlap by something that kind of goes along the middle of both of them? And you can see that this behavior is what we wanted to see. So with this work on a two-body interaction, we'd like to then move to a three-body interaction and then characterize the dynamics of global evolution, talk under global evolutions. And the key takeaways from this is that non-commutation appears everywhere. And we can gain insight into quantum systems by probing non-commutation in classical systems. So with that, that's my work. And I'd like to thank Drs. Alexander LeSchack, Dr. Nicole Younger-Halpern, my advisors, and also Dr. Yushin Wang and Billy Rash for their guidance this summer, as well as the rest of the quantum steampunk group, my MathQuantum and Trend peers, as well as Daniel Serrano, the program director. Thank you.